When humans first looked up at the night sky, they saw pinpoints of light scattered across darkness, stars, planets, and the soft glow of the Milky Way band stretching from horizon to horizon. That luminous river of light has guided explorers, philosophers, and scientists for millennia, but it took centuries before we understood that this shimmering band was not a flat ceiling, but a vast, three-dimensional galaxy composed of hundreds of billions of stars. Mapping this enormous structure has been one of the most challenging endeavors in astronomy, a puzzle with pieces scattered across vast distances, obscured by cosmic dust and moving constantly through space. If you've ever dreamed of reaching the stars, the Milky Way shows just how impossible that is. Spanning over 100,000 light-years, filled with swirling stars, dark dust, and invisible forces, it has no true edge to stand on. We can only map it from afar, piece by piece, tracing its motion through telescopes and radio signals. Subscribe now to explore the cosmos's hidden wonders with us. Early attempts to define the shape of the Milky Way began in the 17th and 18th centuries. Astronomers such as Thomas Wright and Immanuel Kant proposed that the faint milky glow was due to innumerable stars packed together like grains of sand, forming a starry system much larger than the solar system. Yet without powerful telescopes, their ideas remained speculative. By the 1920s, it was still unclear whether the Milky Way was the entirety of the universe or just one of many such systems. It was Edwin Hubble, using the Hooker telescope at Mount Wilson Observatory, who proved that distant, fuzzy patches of light spiral nebulae were actually separate galaxies outside our own. This landmark discovery redefined the Milky Way not as the entire universe, but as one galaxy among billions. Despite Hubble's breakthrough, mapping the Milky Way's structure proved far more difficult than simply identifying other galaxies. From Earth, observations must pass through billions of stars, gas, and dust, which interfere with visible light and make distant regions of the galaxy opaque. For decades, astronomers could only see so far with optical telescopes, relying on indirect clues to infer the galaxy's shape. A major breakthrough occurred with the development of radio astronomy in the mid-20th century. Unlike visible light, radio waves can penetrate dust clouds that block optical telescopes. In the 1950s and 1960s, scientists began mapping the Milky Way by observing radio emissions from neutral hydrogen atoms, the most abundant element in the galaxy. Hydrogen emits radio waves at a specific wavelength of 21 centimeters, and by measuring this radiation across the sky, astronomers could detect vast concentrations of hydrogen gas, even where stars were hidden. One of the pioneers of this work was Harlow Shapley, who earlier in the 20th century had already demonstrated that the Sun was not at the center of the galaxy. Using globular clusters, dense clusters of stars orbiting the galaxy, Shapley estimated that the center of the Milky Way lay in the direction of the constellation Sagittarius and was tens of thousands of light-years away. By the late 20th century, radio mapping revealed a striking picture. The Milky Way was not a random blur of stars, but a flattened disk with spiral arms sweeping regions where stars, gas, and dust are more densely concentrated. These spiral arms, like the Perseus arm, Sagittarius arm, and Scutum Centaurus arm, extend tens of thousands of light-years from the galactic center. Yet even with radio waves, astronomers could only map portions of the galaxy with confidence, because the vast distances, complicated motions, and line-of-sight effects made interpretation difficult. Enter the era of space-based observatories. Launched by the European Space Agency in 2013, the Gaia spacecraft has transformed our understanding of the Milky Way. Unlike ground-based telescopes limited by Earth's atmosphere, Gaia observes from space with extreme precision. Its mission is ambitious: to measure the positions, distances, and motions of more than 1 billion stars in the galaxy, roughly 1% of the total stellar population. to create the most detailed three-dimensional map of the Milky Way ever compiled. To map 1 billion stars with precision, Gaia measures stellar positions to within microarc-seconds units, so small that 1 microarc-second is equivalent to observing a human hair from 1,000 kilometers away. Data from Gaia have revealed intricate details of stellar motion, revealed hidden star clusters, and provided evidence of past galactic collisions that shaped the Milky Way's structure over billions of years. Astronomers pieced together information at different wavelengths: radio, infrared, visible, ultraviolet, and X-rays, each revealing unique aspects of the galactic components. Infrared light, for example, penetrates dust more effectively than visible light, allowing instruments such as the Spitzer Space Telescope and Wide Field Infrared Survey Explorer, or WISE, to observe regions near the galactic center that are otherwise obscured. Yet, even infrared observations have limits. The central region of the Milky Way is densely packed with stars, gas, and dust. This central bulge, extending several thousand light-years across, is so crowded that discerning individual stars becomes challenging. Moreover, the galactic center harbors a supermassive black hole known as Sagittarius A star, with a mass of about 4 million times that of the Sunday. While the black hole itself cannot be seen directly, the motion of nearby stars and flares from hot gas falling into it provide indirect evidence of its presence. The combined observations reveal a barred spiral galaxy with a central bar structure crossing the core, from which spiral arms emanate. The disk of the Milky Way spans roughly 100,000 light-years in diameter, with a thickness of about 1,000 light-years in the stellar disk and much thicker when accounting for the halo of older stars and globular clusters surrounding it. The Milky Way remains partially obscured because we are inside it. The densest parts of the galaxy block our view, and the distant edges both toward the galactic rim and into the halo are challenging to observe. Astronomers also map the distribution of stars by studying their motion. Stars do not sit still. They orbit the galactic center at speeds of hundreds of kilometers per second. These motions can distort signals and make distance measurements tricky. To overcome this, scientists measure the Doppler shifts in light and radio waves, changes in frequency caused by motion toward or away from us, to estimate velocity. Combining velocity data with positional measurements allows astronomers to infer the location and density of stars across the galaxy. The Milky Way is slowly merging with smaller galaxies that have been gravitationally captured. Streams of stars, remnants of these past mergers, can be seen in the halo, providing data on the galaxy's evolutionary history. The Sagittarius dwarf elliptical galaxy, discovered in 1994, is one such example, currently being pulled apart as it orbits and merges with the Milky Way. These interactions redistribute stars and influence the structure of the spiral arms and the motion of stars in the outer regions. Mapping efforts indicate that the Milky Way's outer disk is warped, with its outer regions bending upward and downward. This warping is thought to result from gravitational interactions with nearby galaxies, including the large and small Magellanic Clouds, two dwarf galaxies orbiting the Milky Way. Observations show how stars are born in dense clouds, travel vast orbits, interact gravitationally, and how dark matter, an invisible form of matter that outweighs visible stars by a factor of 5 to 1, influences the motion of the galaxy on the largest scales. There are regions where dust and gas are so opaque that even infrared and radio observations struggle to penetrate. Some star populations are so distant and faint that they elude detection. Astronomers still debate the exact number of spiral arms, the shape of the galactic bar, and the full extent of the halo, based on available observations from within the galaxy. Ongoing observations and improved tools continue to provide more detailed information about the Milky Way, including its structure, stellar motions, and galactic components. Spiral Secrets: Understanding the Structure of Our Galaxy. When astronomers first realized that the Milky Way was not just a flat band of light, but a sprawling island of stars, one of the first questions they faced was deceptively simple. What shape does our galaxy have? Early views pictured it as a uniform disk, but as observational technology improved, especially through radio and infrared surveys, it became clear that the Milky Way is a richly structured system with distinct components. Understanding the galaxy's structure is essential not only for mapping it, but also for grasping why the idea of reaching the edge is profoundly complicated. The Milky Way's structure is often described in terms of spiral arms, a central bulge, a bar, a disk, and an extended halo. One of the foundational insights into this structure came from studying how stars and gas are distributed across the galaxy. Unlike a smooth distribution, stars cluster in patterns long, curved chains of higher density that we call spiral arms. These arms are not rigid structures like the spokes of a wheel. Rather, they are regions where stars and gas are temporarily compressed as they orbit the center. Over time, astronomers have identified several major spiral arms in our galaxy. The Perseus arm lies between 6,000 and 13,000 light-years from the galactic center and is populated with giant molecular clouds where new stars form. The Sagittarius arm lies closer, between roughly 5,000 and 10,000 light-years from the center, and contains many bright star-forming regions, including the massive nebula known as the Lagoon Nebula. There is also the outer arm, further out than the Perseus arm, and then smaller features named the Local arm, where our Sun resides, and the Centaurus arm. These arms are not static patterns etched into the galactic disk. They arise from what astrophysicists call density waves, patterns of gravitational compression that propagate through the disk, triggering star formation as they sweep through gas clouds. As a result, the stars we see clustered in the arms are often younger and brighter than stars in other parts of the galaxy. Clusters of young stars mark these arms temporarily, while the density wave moves through the gas. At the center of the galaxy lies a region vastly different from the spiral arms of the disk. Instead of a flat distribution of stars, the central region forms a bulge, a roughly spherical concentration of older stars. Observations show that this bulge extends several thousand light-years in diameter and contains some of the oldest stars in the Milky Way. These stars have ages of 10 billion years or more, predating much of the star formation found in the disk. The concentration of stars toward the center is so dense that individual stars are difficult to resolve even with powerful telescopes. At the very heart of the bulge resides a supermassive black hole known as Sagittarius A star. While invisible directly, its presence is revealed by the motion of stars orbiting around it at tremendous speeds. Some of these stars complete orbits in just a few decades, tightly bound by a mass estimated at 4 million times that of our Sun. This black hole influences the dynamics of stars in its immediate neighborhood. Outside the spiral arms and central bulge lies the galactic disk. This disk is where the majority of the Milky Way's stars reside, from massive blue giants to long-lived red dwarfs like Proxima Centauri, located more than 4 light-years from Earth. The disk has a thickness of roughly 1,000 light-years, much thinner compared to its diameter of about 100,000 light-years. Most of the gas and dust that fuel star formation are concentrated in this thin plane. Yet beyond this relatively thin plane is a vast, diffuse region known as the halo. The halo extends far beyond the visible disk, reaching distances of at least 300,000 light-years from the galactic center. Its stars are much more sparsely distributed, and they tend to be older, metal-poor stars that formed in the early history of the galaxy or were captured through past collisions with smaller galaxies. Scattered throughout the halo are globular clusters, compact assemblies of hundreds of thousands of stars bound tightly by gravity. One of the largest known clusters, Omega Centauri, contains millions of stars and is itself thought to be the remnant core of a dwarf galaxy consumed by the Milky Way long ago. The halo is also where dark matter, a mysterious, invisible component of the universe, exerts its influence most dominantly. Unlike stars and gas, dark matter does not emit or absorb light, but its gravitational effect on the motion of stars and gas throughout the galaxy reveals its presence. Measurements of how stars orbit in the outer disk show velocities that cannot be explained by visible matter alone. This implies that the Milky Way is embedded in a massive halo of dark matter that outweighs the combined mass of all visible stars by a factor of 5 to 1. While the halo itself is nearly invisible, its gravitational signature is a major factor in shaping the galaxy's structure and dynamics. Another structural feature that emerged from detailed surveys is the discovery of a bar crossing the galactic center. Early observations could not definitively confirm this bar, but infrared mapping revealed an elongated distribution of stars extending across the central region. Bars are common in spiral galaxies and act as mechanisms that funnel gas inward toward the central bulge. This can trigger bursts of star formation and influence the spiral arm pattern. In the Milky Way, the bar is estimated to stretch about 27,000 light-years across, almost as wide as the distance from Earth to the galactic center. The Milky Way consists of spiral arms, a central bulge, a bar, disk, and halo. Certain vantage points are blocked by dust lanes, and distant regions appear warped or distorted due to perspective effects. The outer disk of the Milky Way is warped and twisted. The outermost regions bend up and down, influenced by the gravitational tug of neighboring satellite galaxies, notably the Large and Small Magellanic Clouds. These two dwarf galaxies orbit the Milky Way, and their gravitational pull disturbs the disk's outer edges. Precise measurements show that the warp has an amplitude of several thousand light-years. Extensive mapping efforts have revealed stellar streams, long, narrow filaments of stars that arc across the sky. These streams are remnants of dwarf galaxies and globular clusters that ventured too close to the Milky Way and were torn apart by tidal forces. The Sagittarius stream, for example, wraps around the galaxy in a sprawling loop, evidence of past mergers that contributed stars to the halo. The spiral arms fade gradually into the outer reaches of the disk, and beyond that, the halo's slow decline in star density makes it difficult to define a clear boundary. Clusters, streams, and distant stars extend beyond the main disk. Stars orbit the galactic center at speeds that vary with their distance, and regions like the bar can channel material inward, altering the distribution of mass over time. Future observatories, both on the ground and in space, will provide higher resolution maps, deeper surveys of faint stars, and improved measurements of dark matter's influence. How big is big? Measuring the Milky Way. Measuring the Milky Way galaxy has been one of astronomy's most persistent challenges, a quest that defies ordinary intuition because we are trying to gauge the size of something we are inside of, not outside looking in. Early astronomers struggled to define the Milky Way's boundaries because the galaxy extends not only in visible stars, but also in diffuse gas, dust, and an invisible component called dark matter. Determining how big the Milky Way truly is requires piecing together information from many kinds of observations, from radio waves to stellar motions, and even the behavior of the smallest detectable objects in the halo. In the early 20th century, astronomers estimated the size of the Milky Way using star counts and observations of star clusters. Harlow Shapley, mentioned in the previous chapter for locating the galactic center, also attempted one of the first size measurements using globular clusters, dense collections of stars orbiting the galaxy. Shapley found that these clusters were not evenly distributed around Earth, which suggested that our location was offset from the galactic center. By estimating distances to these clusters, Shapley concluded the Milky Way's diameter was about 300,000 light-years. Later observations revealed that this estimate was too large, but Shapley's method laid the groundwork for understanding our place within the galaxy. Through the decades, improvements in telescopes and observational techniques have dramatically refined our picture of the Milky Way's dimensions. Today, astronomers generally agree that the visible disk of our galaxy spans roughly 100,000 light-years across. At a speed of 1 million miles per hour, far faster than any human-made object, it would still take tens of thousands of years to travel from one side of the disk to the other. Stars and gas are concentrated in the thin disk, and the galaxy also contains an extended halo of older stars and globular clusters that stretches much farther out. Some estimates place the halo's radius at more than 300,000 light-years. Loosely bound stars and stellar remnants influenced by the Milky Way's gravity extend beyond the bright disk. The halo's outer boundary is not sharply defined. Star density gradually decreases with distance, blending into the space between galaxies. One pivotal method for measuring galactic scale involves observing how stars move. In a system like the Milky Way, stars in the outer regions orbit the center at high speeds. These orbital speeds are surprisingly constant over large distances, an observation that puzzled astronomers in the 1970s and led to the discovery of dark matter, a mysterious substance that does not emit light but exerts gravitational influence. Although dark matter is invisible, its gravitational effects allow astronomers to infer the true mass of the galaxy far beyond the visible stars. Based on these motions, the Milky Way's total mass, including stars, gas, dust, and dark matter, is now estimated to be about 1.5 trillion times the mass of the Sun. Remote sensing of hydrogen gas also helps map the Milky Way's size. Neutral hydrogen emits a characteristic radio signal that can be detected across vast distances, even through dust clouds that block visible light. By measuring this emission at different wavelengths, astronomers determine how far away gas clouds are and how they move. Surveys such as the Leiden-Argentine Bonn, or LAB survey, have measured hydrogen emission across the entire sky, revealing the sprawling extent of gas in the galaxy. These hydrogen maps show that gas, and by extension the mass of the galactic disk, extends to well beyond the regions where most stars reside. Space telescopes have also played a crucial role. Infrared observatories like the Spitzer Space Telescope and the Wide Field Infrared Survey Explorer have mapped stars in the inner galaxy where dust obscures visible light. These surveys have revealed a central bar structure and traced the spiral arms deeper into dusty regions. Infrared light penetrates dust more effectively, allowing astronomers to count stars in dense regions near the galactic center and refine estimates of how many stars the Milky Way contains. Current estimates suggest there are between 200 billion and 400 billion stars within the galaxy, though the exact number remains uncertain because many faint, low-mass stars are difficult to detect. While the spiral arms lie in a relatively thin plane about 1,000 light-years thick, a component called the thick disk contains older stars that extend several thousand light-years above and below the central plane. The thick disk contains older, metal-poor stars. Mapping the Milky Way's size involves measuring distances to stars. The Gaia mission has measured positions and distances to more than 1 billion stars with high precision. Gaia data reveal warps in the disk and streams of stars moving in coherent patterns. By knowing the distances and motions of stars, scientists can reconstruct a three-dimensional map of the galaxy. Gaia data show that the galactic disk is not uniformly flat. At large distances from the center, the disk bends up and down in a warped shape. This warp results from gravitational interactions with satellite galaxies, such as the large and small Magellanic Clouds, which tug on the outer disk as they orbit the Milky Way. The warp affects measurements of the galaxy's vertical size because different regions of the disk are at different heights above the central plane. Surveys of faint dwarf stars and distant star clusters indicate that the stellar disk could extend to as far as 120,000 light-years from the center. In addition, tenuous gas and dark matter likely stretch even farther. Some studies suggest that the Milky Way's gravitational influence extends almost 500,000 light-years, encompassing regions populated only by faint stars or star streams from disrupted dwarf galaxies. Surveys of faint dwarf stars and distant star clusters indicate that the stellar disk could extend to as far as 120,000 light-years from the center. In addition, tenuous gas and dark matter likely stretch even farther. Some studies suggest that the Milky Way's gravitational influence extends almost 500,000 light-years, encompassing regions populated only by faint stars or star streams from disrupted dwarf galaxies. Satellite galaxies also play a role in defining the Milky Way's zone of influence. The Large Magellanic Cloud, or LMC, and Small Magellanic Cloud, on SMC, are two of the most prominent companions, located about 160,000 and 200,000 light-years away, respectively. These dwarf galaxies are close enough to experience tidal forces from the Milky Way's gravity, and their motions help astronomers refine models of the galaxy's mass distribution. Beyond the Magellanic Clouds are dozens of other faint dwarf galaxies and stellar streams, some recently discovered by deep surveys. These distant objects blur the line between the galaxy's outskirts and the local group, the collective of galaxies that includes Andromeda and dozens of dwarf companions. All these methods, stellar motions, hydrogen mapping, infrared surveys, satellite data, and Gaia measurements, help build a composite picture of the Milky Way's size. Yet every technique has limitations, and reconciling different datasets remains an ongoing effort. For example, measuring distances to the farthest stars becomes progressively harder the dimmer and farther they are, introducing uncertainties that can only be reduced with improved instruments and observation time. The Andromeda Galaxy, our nearest large neighbour, spans about 220,000 light-years in visible diameter, more than twice the size of the Milky Way's bright disk. The Milky Way's extended halo might rival or surpass Andromeda's in mass and reach. Measurements of stars, gas clouds, and distant globular clusters provide information to determine the Milky Way's size. It is a system of stars, gas, dust, and dark matter, with its gravitational influence extending far beyond the visible disk. The Sun's place, our cosmic neighborhood. Nestled within one of the Milky Way's spiral arms lies our solar system, a seemingly ordinary corner of a galaxy that stretches across 100,000 light-years. Yet understanding exactly where the Sun resides and the environment it inhabits is far from trivial. Our location is not central, not on the outskirts, but somewhere in the middle, offering both a unique vantage point and a set of challenges for mapping and comprehending the galaxy. The Sun's neighborhood may seem quiet compared to the bustling central bulge, but it is full of subtle complexity that reveals the motions, structures, and histories of stars around us. The Sun is situated in the local arm, a minor spiral arm sometimes referred to as the Orion arm. This arm lies between the larger Sagittarius arm and Perseus arm, and stretches roughly 3,500 light-years across. Our solar system is about 27,000 light-years from the galactic center, orbiting it at an average speed of roughly 828,000 kilometers per hour, completing a single orbit every 225 to 250 million years. Surrounding the Sun is an area astronomers call the local bubble, a low-density cavity of hot, ionized gas spanning roughly 300 light-years. This bubble was likely created by multiple supernova explosions over the past 10 to 20 million years. Within this bubble, interstellar material is relatively sparse compared to the denser clouds that populate the spiral arms. This lower density has shielded the solar system from frequent encounters with massive gas clouds, which could have disrupted planetary orbits or increased cosmic radiation exposure. Even so, remnants of past supernovae still linger, evidenced by traces of iron 60 found in Earth's crust, a rare isotope created in supernovae. The nearest stars provide another aspect of our neighborhood. The closest star system, Alpha Centauri, lies 4.37 light-years away and consists of 3 stars, Alpha Centauri A and B, which form a binary pair, and Proxima Centauri, a red dwarf with at least one known exoplanet. Beyond this, other nearby stars, such as Barnard's star, Wolf 359, and Lalande 21185, populate a region within about 10 light-years. These stars collectively form part of the Sun's moving group, a set of stars sharing similar motion through space. One feature of the Sun's environment is its motion relative to surrounding stars. While orbiting the galactic center, the Sun also exhibits vertical oscillations above and below the galactic plane, moving approximately 70 light-years above or below over cycles of about 60 million years. These vertical motions carry the solar system through regions of differing star density. Star-forming regions near the Sun include the Orion Molecular Cloud Complex, about 1,350 light-years away. This vast region of gas and dust contains nebulae like the Orion Nebula and Barnard's Loop, sites of active star formation where new stellar systems emerge over tens of thousands of years. These regions show processes such as the formation of protoplanetary disks, the accretion of gas and dust, and the initial clustering of young stars. The Sun's neighborhood hosts a population of older stars known as the thick disk stars. These stars generally have lower metallicity, fewer elements, heavier than helium, indicating they formed earlier in the Milky Way's history. Many of these stars travel on more elliptical orbits, passing in and out of the Sun's region over millions of years. Beyond stars, the solar neighborhood contains numerous remnants of stellar evolution. White dwarfs, neutron stars, and even isolated black holes are scattered throughout the region, though many remain undetectable except through indirect observation. Occasionally, close encounters with these objects could perturb the Oort cloud, the distant shell of icy bodies surrounding the solar system, potentially sending comets toward the inner planets. Interstellar gas and dust in the vicinity of the Sun is not uniformly distributed. Dense clouds, like the Taurus Molecular Cloud, about 430 light-years away, and the Chamaeleon Complex, around 500 light-years distant, punctuate the region with pockets of higher density. These clouds serve as raw material for future generations of stars and planets, and their chemical composition reveals the abundance of elements forged in prior generations of stars. Mapping these clouds provides data on the star formation history of the local region. One discovery about the Sun's neighborhood comes from studying stellar streams, remnants of dwarf galaxies disrupted by the Milky Way's gravity. The Helmi stream, for instance, consists of stars passing through the solar neighborhood but originating from a dwarf galaxy absorbed by the Milky Way billions of years ago. These streams move at different velocities and angles. Understanding the Sun's place also requires observing the galactic magnetic field. Though invisible, this field threads through the disk and spiral arms, influencing the motion of charged particles, including cosmic rays. Locally, the magnetic field is relatively weak, about 2 to 5 microgauss, but it plays a role in shaping interstellar clouds, guiding cosmic rays, and even protecting the solar system from some incoming high-energy particles. Observations of nearby exoplanets add another layer of data. Over 5,000 exoplanets have been confirmed in the Milky Way, with dozens located in stars less than 50 light-years from the Sun. Systems such as Tau Ceti and Epsilon Eridani host multiple planets, some potentially within habitable zones. Even our motion, relative to the cosmic microwave background, the faint afterglow of the Big Bang, shows that the solar system is moving at approximately 370 kilometers per second toward the constellation Leo. This motion, combined with orbital and vertical oscillations, provides a reference for measuring velocities of other objects in the galaxy. The solar neighborhood contains star density variations, molecular clouds, stellar remnants, stellar streams, magnetic fields, and planetary systems. The local arm, including the local bubble, contains diverse stellar populations and interstellar structures. Astronomers study the Sun's location to observe the structure and motion of nearby stars and interstellar material. A journey through the galaxy would pass through regions of varying star density, gas clouds, and interstellar material, influenced by the gravitational effects of nearby stars and satellite streams. Astronomers examine nearby stars, gas clouds, and stellar remnants to study the Milky Way's structure and dynamics. Observations trace star motion, gas flow, and how local structures relate to the larger galaxy. The Milky Way's regions are all in motion, affected by gravitational forces spanning thousands of light-years. The Sun is located in a spiral arm that is neither at the center nor at the periphery, orbiting amidst a population of stars, gas clouds, and stellar remnants, all moving and interacting over millions of years. The solar neighborhood represents a small portion of the Milky Way, whose full boundaries extend far beyond the local region. Riding the galactic conveyor stellar motion and rotation, the stars in our galaxy are far from stationary. While it might appear that the night sky is a static canvas, in reality, every star is on a complex journey, moving through the Milky Way under the influence of gravity, past collisions, and invisible forces. The concept of stellar motion is central to understanding why the galaxy has no definitive edge, and why reaching one, even in theory, is an almost unimaginable challenge. It also explains the dynamic environment in which our Sun and solar system reside. Stars orbit the center of the galaxy at a wide range of speeds, depending on their distance from the core. Objects near the center move more rapidly due to the intense gravitational pull of the supermassive black hole, Sagittarius A star, as well as the densely packed stars and gas in the bulge. Stars further out in the disk orbit more slowly in terms of angular speed, but many still achieve hundreds of kilometers per second relative to the galactic center. The Sun, for example, travels at approximately 828,000 kilometers per hour, completing a single orbit roughly every 225 to 250 million years. This orbit is not a perfect circle. It is slightly elliptical and influenced by the gravitational tug of neighboring stars, spiral arms, and satellite galaxies. The motion of stars is influenced by more than just the galactic center. The Milky Way's spiral arms act as density waves, regions where stars temporarily slow down and compress before moving on. This creates the illusion that the arms are rigid, when in reality stars continuously move in and out. These waves also trigger bursts of star formation as they compress gas clouds, giving rise to bright, young stars that populate the arms for tens or hundreds of millions of years before dispersing. Stars in the halo exhibit even more unusual motion. Many of these stars follow highly elliptical, inclined orbits that take them thousands of light-years above and below the galactic plane. These trajectories are remnants of past galactic mergers, capturing stars from smaller galaxies absorbed into the Milky Way. One prominent example is the Sagittarius stream, a massive ribbon of stars stretching across the sky, which originated from the Sagittarius dwarf elliptical galaxy. The stars in this stream move at speeds of several hundred kilometers per second. Clusters of stars also move in characteristic ways. Globular clusters, for instance, orbit the galaxy in the halo, with some traveling at speeds exceeding 200 kilometers per second. Omega Centauri, one of the largest and most massive globular clusters, contains millions of stars orbiting the Milky Way's center, with stars at varying velocities, producing a complex internal dynamical structure. Astronomers use these motions to estimate the mass distribution of the galaxy, including contributions from dark matter. Proper motion, the apparent angular movement of stars across the sky as seen from Earth, provides another window into stellar dynamics. Nearby stars often display measurable motion within just a few decades of observation. Barnard's star, located 5.96 light-years away, exhibits the largest known proper motion, shifting nearly 10.3 arc-seconds per year. Observing proper motion allows astronomers to reconstruct the past and future paths of stars, estimate gravitational influences, and trace the evolution of local stellar populations over millions of years. Interstellar clouds of gas and dust, although much less dense than stars, are also carried along by galactic rotation. Molecular clouds in star-forming regions such as the Orion Complex and the Carina Nebula are influenced by spiral arm dynamics and local gravitational perturbations. These clouds move at velocities comparable to nearby stars, and their internal turbulence and collisions affect star formation patterns. Beyond stars and clouds, the Milky Way contains streams of debris left over from disrupted dwarf galaxies. These stellar streams follow coherent paths across vast distances. For example, the Helmi stream, located in the solar neighborhood, consists of stars moving together at high velocities, remnants of a dwarf galaxy swallowed over 6 billion years ago. These streams contribute to the galaxy's overall gravitational field, affecting the orbits of other stars. Dark matter plays a decisive role in stellar motion, particularly in the outer disk and halo. Observations show that stars far from the galactic center orbit at nearly constant velocities, defying what would be expected if only visible matter contributed to gravity. This flat rotation curve phenomenon led to the conclusion that the Milky Way is embedded in a massive, invisible halo of dark matter, extending well beyond the visible disk. Dark matter shapes the paths of stars, stellar streams, and even globular clusters, meaning that the motion of every object we observe is a product of both visible and unseen gravitational forces. Within the disk, stars exhibit differential rotation, meaning that stars closer to the center complete orbits faster than those farther out. This differential motion causes spiral arms to wind slowly and can also stretch stellar associations into elongated patterns. Over billions of years, differential rotation redistributes stars across the disk. Even the Sun experiences subtler motions superimposed on its galactic orbit. It oscillates vertically above and below the galactic plane approximately every 60 million years, moving about 70 light-years above or below the central plane. The solar neighborhood, though relatively calm compared to the inner galaxy, is not static. Clusters within the disk, such as open clusters, also display collective motion. The Pleiades, located about 444 light-years from Earth, and the Hyades, around 153 light-years away, both travel through the disk, gradually dispersing their member stars over tens or hundreds of millions of years. Observing these motions allows astronomers to test models of disk dynamics and estimate how stars migrate through different regions of the galaxy. Galactic rotation also affects interstellar magnetic fields, which thread through the disk and influence charged particles, gas clouds, and cosmic rays. The motion of stars and gas within the magnetic field generates complex interactions, including localized turbulence, cosmic ray acceleration, and shaping of molecular clouds. Every star, cluster, and cloud is moving, and the outer halo blends gradually into intergalactic space. Stars may move thousands of light-years over millions of years, resulting in a diffuse outer boundary shaped by dynamics, mergers, and gravitational interactions. Even the motions of satellite galaxies affect stellar paths. The Large Magellanic Cloud, Small Magellanic Cloud, and numerous dwarf galaxies tug on the Milky Way, subtly influencing the orbits of stars, gas clouds, and streams. These gravitational interactions can induce waves, bends, and ripples in the disk, creating regions where stars accelerate or decelerate, and sometimes generating tidal streams that extend hundreds of thousands of light years. Stars, clouds, and streams traverse the galaxy at high speeds, while gravitational forces guide their paths and interactions. Astronomers measure velocities, proper motion, and orbital patterns to determine the scale and dynamics of the Milky Way. Through clouds of dust, obstacles in the interstellar medium, traveling through the Milky Way is far from a straightforward path. Even if a spacecraft could move at unimaginable speeds, the interstellar medium presents obstacles that complicate any journey toward the galaxy's outer regions. The space between stars is not empty. It is filled with gas, dust, cosmic rays, and magnetic fields that together create a complex, sometimes hostile environment. Understanding these components is crucial for grasping why reaching the edge of the Milky Way is not only a matter of distance, but also of navigating a dynamic and obstructed medium. The interstellar medium, or ISM, consists primarily of hydrogen and helium, with trace amounts of heavier elements such as carbon, oxygen, and iron. Hydrogen exists in multiple forms: neutral atomic hydrogen, HIIized hydrogen, HII, and molecular hydrogen, H2, each occupying distinct regions and temperatures. HI regions typically have temperatures around 100 Kelvin and are found in diffuse clouds spanning tens to hundreds of light years, while HII regions are hotter, often exceeding 10,000 Kelvin, created by the ionizing radiation of massive young stars. Molecular clouds, on the other hand, are cold, dense regions where temperatures drop to just 10 Kelvin, forming stellar nurseries that birth new generations of stars. Dust grains, although comprising only about 1% of the interstellar medium by mass, play an outsized role in shaping the environment. These microscopic particles, made of silicates, carbon, and ice, absorb and scatter light, creating dark lanes that obscure distant stars from view. Iconic structures such as the Horsehead Nebula in Orion or the Dark Rift in the Milky Way's plane are direct manifestations of dense dust clouds blocking starlight. These clouds, often tens of light years in size, create visual and navigational barriers, making certain regions of the galaxy effectively invisible in optical wavelengths. High-density molecular clouds are particularly significant obstacles. Some, like the Taurus Molecular Cloud and the Rho-Ophiuchi Cloud Complex, contain thousands of solar masses of gas and dust, forming a tangled web that any hypothetical journey would need to traverse. Within these clouds, temperatures are low, but turbulence can produce shock waves and density variations capable of compressing pockets of material into new stars. These processes illustrate that the ISM is not static, but is constantly evolving, with structures forming, dispersing, and interacting on timescales of millions of years. Supernovae add another layer of complexity. When massive stars explode, they send shockwaves rippling through the interstellar medium, heating gas to millions of degrees and accelerating cosmic rays. These supernova remnants, such as the Veil Nebula in Cygnus or the Crab Nebula in Taurus, not only inject energy into the surrounding medium, but also chemically enrich it with elements like iron, calcium, and silicon. A star traveling through the galaxy could encounter these high-energy regions, where radiation levels are extreme and collisions with particles could damage spacecraft or biological life. The interstellar medium also hosts magnetic fields, threading through the galaxy in both the disk and halo. These fields influence the motion of charged particles, shape molecular clouds, and create pressure that counteracts gravitational collapse. Locally, the Milky Way's magnetic field is relatively weak, around 2 to 5 microgauss, but even this modest strength can affect cosmic ray propagation and the alignment of dust grains. Magnetic fields create regions where movement is constrained or redirected, adding another layer of complexity for any hypothetical navigation through the ISM. Cosmic rays themselves pose a hazard. Traveling near the speed of light, these charged particles originate from supernova explosions and other high-energy events. They permeate the galaxy, bombarding stars, planets, and spacecraft alike. Even within the solar system, Earth's magnetic field and atmosphere provide protection. But in the open interstellar medium, exposure to cosmic rays can be intense, with energies reaching up to 10-20 electron volts. Any object attempting to traverse thousands of light-years of interstellar space would be continually bombarded, and shielding against these particles at sufficient levels would be a monumental engineering challenge. Interstellar turbulence adds yet another factor. Gas and dust are rarely stationary. Shock waves from stellar winds, supernovae, and differential rotation of the galaxy stir the medium, creating eddies and filaments that shift over time. These turbulent motions can reach speeds of tens of kilometers per second, redistributing matter and forming complex density patterns that change on timescales shorter than the orbit of the Sun around the galactic center. For a star or spacecraft moving through this environment, these constantly shifting clouds represent both obstacles and hazards. Large-scale structures in the ISM, such as superbubbles, span hundreds of light-years and are created by the combined effects of multiple supernovae and stellar winds. The local bubble in which the solar system resides is one example, extending roughly 300 light-years. Surrounding it are denser regions, like the Lupi bubble, created by past supernova activity in the Scorpius-Centaurus association. These large cavities of low-density gas are bordered by high-density shells, meaning that navigating between low-density zones could require passing through turbulent, high-pressure boundaries filled with shocked gas. Even at the outer edges of the Milky Way's disk, the ISM remains present, though increasingly tenuous. Neutral hydrogen can be detected, extending tens of thousands of light-years beyond the visible stars. These distant clouds are influenced by tidal forces from satellite galaxies, like the Large Magellanic Cloud, creating streams and filaments that ripple across the galaxy. Such structures illustrate that the interstellar medium does not end abruptly at a defined galactic edge, but gradually blends into the intergalactic medium, further complicating any notion of a sharp boundary. Dust and gas also interact with light and radiation in ways that affect observation and measurement. Interstellar reddening occurs as dust scatters blue light more effectively than red, making distant stars appear redder than they truly are. This effect must be accounted for in distance measurements and in mapping galactic structure, but it also highlights how pervasive the ISM is. Even faint clouds, invisible to the naked eye, can distort light across hundreds of light-years, influencing how we perceive the galaxy's shape and scale. Finally, chemical complexity in the ISM is remarkable. Observations using radio telescopes have identified over 200 molecules, from simple diatomic species like carbon monoxide to complex organic compounds such as amino acids. These molecules form in the cold, dense cores of molecular clouds and provide the raw materials for future planetary systems. The distribution of these compounds is uneven, shaped by turbulence, shocks, and radiation, illustrating that the medium is a dynamic chemical laboratory stretching across the Milky Way. The interstellar medium consists of gas, dust, turbulence, magnetic fields, and radiation distributed throughout the galaxy. Even at distances far from the dense spiral arms or central bulge, these components remain present, forming a continuum of matter that gradually transitions into the intergalactic medium. The ISM varies in density, composition, and motion across regions of the galaxy. Clouds, bubbles, and filaments are widespread throughout the Milky Way. Gas, dust, magnetic fields, and radiation are present across different regions, influencing star formation and the chemical composition of the interstellar medium. These components gradually decrease in density toward the outskirts of the galaxy, transitioning into the intergalactic medium. Gravity's grip, the Milky Way's mass distribution. The Milky Way is not just a collection of stars and gas, it is a vast gravitational web woven from visible matter, dark matter, and the central supermassive black hole. Understanding the galaxy's mass distribution is crucial for grasping why reaching its edge is physically impossible. Gravity does not act uniformly. It varies depending on location, density, and the unseen influence of dark matter. Every star, planet, and cloud moves under its complex pull, creating a dynamic system in which even light-speed travel would be insufficient to escape the galaxy's grip. At the center of the Milky Way lies Sagittarius A star, a supermassive black hole with a mass of roughly 4 million times that of the Sun. Despite its relatively small size compared to the galaxy, its gravitational influence dominates the central parsecs, controlling the orbits of nearby stars. Observations of stars like S2, which pass within 17 light hours of the black hole, have allowed astronomers to precisely measure Sagittarius A star's mass and to confirm predictions of general relativity. Stars in the central bulge orbit at speeds exceeding 1,000 kilometers per second, tightly bound by the immense gravity concentrated in this small volume. Surrounding the central bulge is the galactic disk, home to the spiral arms and most of the Milky Way's stars. The disk contains between 60 and 80 billion solar masses of stars and hundreds of billions of solar masses of gas and dust. Its density decreases with distance from the center, but this decrease is not smooth. Spiral arms act as regions of slightly enhanced density, where stars, gas, and molecular clouds cluster, creating gravitational wells that influence stellar orbits. Stars closer to the galactic center orbit faster than those at the outer edges, a phenomenon known as differential rotation. And this variation in motion is a direct consequence of mass distribution. Beyond the visible disk, the Milky Way is enshrouded in a halo populated by older stars, globular clusters, and dark matter. Globular clusters like Omega Centauri, containing millions of stars, orbit the galaxy in extended, elliptical paths that take them tens of thousands of light years above and below the disk. Many of these clusters originated from smaller galaxies, absorbed over billions of years. Their motion is influenced by both visible mass and the dark matter halo, which dominates gravitational effects at large distances. Dark matter is perhaps the most enigmatic component of the Milky Way's mass. While invisible, its presence is inferred from the flat rotation curve of the galaxy. Stars far from the center orbit at nearly the same velocity as those closer in, despite the decline in visible mass. This requires a vast halo of matter extending well beyond the disk, containing several times the mass of all visible stars, combined likely between 1 and 2 trillion solar masses. This dark matter halo binds the galaxy together, preventing stars at the outer edges from escaping and ensuring that the Milky Way's gravity remains significant even thousands of light years beyond the disk. Gas and dust also contribute to the gravitational landscape. Giant molecular clouds, each containing thousands to millions of solar masses, create localized gravity wells, subtly perturbing the orbits of nearby stars. These clouds are concentrated along the spiral arms, but also appear as isolated clouds in the halo. In addition, high-velocity clouds of hydrogen move through the outer regions, their paths shaped by both the visible mass of the disk and the invisible pull of dark matter. The combination of stars, gas, dust, and dark matter forms a gravitationally complex environment in which trajectories are constantly altered. Even within the solar neighborhood, the influence of mass is evident. The Sun's orbit is affected by nearby stars, molecular clouds, and the larger mass distribution of the disk and halo. Vertical oscillations above and below the galactic plane, occurring roughly every 60 million years, are a direct response to gravitational forces from the dense stellar disk and halo mass. These motions result from the cumulative gravitational forces exerted by stars, gas, and dark matter in the local region. Tidal forces are another critical aspect of mass distribution. As satellite galaxies, such as the Large and Small Magellanic Clouds, orbit the Milky Way, they induce tidal interactions that warp the disk and redistribute gas and stars. Streams of stars, remnants of dwarf galaxies torn apart by tidal forces, trace the contours of the gravitational potential. The Sagittarius stream, extending over tens of thousands of light-years, is an example of tidal effects on stellar motion far beyond the visible disk. The gravitational pull of the Milky Way also governs the limits of the interstellar medium. Gas clouds, cosmic rays, and dust particles all remain bound within the galaxy, moving along paths defined by the mass distribution. The outer halo, though extremely sparse, still retains gas and star clusters under the galaxy's gravitational influence. Even at distances exceeding 100,000 light-years from the center, gravity shapes motion, ensuring that nothing simply drifts freely into intergalactic space without immense energy to escape. Mass distribution also affects potential travel corridors. There is no straight path free of gravitational influence. A star or spacecraft attempting to move outward encounters changing gravitational forces from the central bulge, spiral arms, molecular clouds, and the dark matter halo. Each gravitational well alters the path, requiring enormous energy to maintain a steady course. Unlike planets in the solar system, where gravity is concentrated in a few massive bodies, the galaxy's mass is diffuse yet cumulative, creating a pervasive, unavoidable gravitational environment. Observations using instruments like the Gaia satellite have revolutionized understanding of mass distribution. By measuring positions and velocities of over 1 billion stars, astronomers can model the gravitational potential of the Milky Way in unprecedented detail. These models confirm the presence of dark matter, quantify the disk and bulge mass, and reveal subtle perturbations caused by spiral arms and satellite interactions. The data show that the Milky Way is not a static structure. Gravity continuously redistributes matter, shifting the location of stars and clouds over millions of years. In addition, local density variations create dynamic gravitational turbulence. As stars orbit, they encounter regions of enhanced mass that slightly deflect their paths. These cumulative deflections, though small, add up over millions of years, illustrating that the galaxy is a gravitational labyrinth rather than a uniform plane. For any hypothetical voyager, these perturbations mean that a straight line to the edge does not exist. Every trajectory would be continuously curved and redirected. Even at the galactic outskirts, gravity remains significant. The dark matter halo ensures that stars and clouds at distances exceeding 150,000 light-years remain bound. The galaxy gradually transitions into intergalactic space, but this boundary is not sharply defined. Gravitational influence extends over enormous distances, fading slowly yet remaining a factor for any moving object. To escape entirely would require energy far beyond current technological capability. The Milky Way's mass distribution includes the central supermassive black hole, the disk, the halo, and the dark matter component. Gravity influences the motion of stars, gas, and dust across the galaxy. Gravitational effects extend well beyond visible stars, affecting objects in the outer halo. Gravity interacts with gas, dust, radiation, and the interstellar medium throughout the Milky Way. Mass distribution, including visible and dark matter, affects the motion of stars, gas clouds, and other objects, creating a complex gravitational environment across the galaxy. Black holes and stellar hazards. Beyond the invisible web of gravity that binds the Milky Way lies a dangerous landscape filled with extreme stellar phenomena. Even if one could somehow navigate through dust, gas, and dark matter, there remain countless hazards capable of destroying anything that ventures too close. Black holes, neutron stars, supernova remnants, and rogue stellar objects form a network of perils that makes traveling to the outer reaches of the galaxy a deadly endeavor. These are not mere curiosities. They shape the structure, evolution, and motion of stars throughout the Milky Way. At the heart of the galaxy, Sagittarius A star dominates the center, a supermassive black hole with a mass of around 4 million suns compressed into a region smaller than our solar system. Its gravitational pull is so intense that stars like S2, orbiting just 17 light-hours away, travel at speeds exceeding 7,650 kilometers per second during their closest approach. Beyond this radius, however, its influence blends with that of the surrounding bulge. Close encounters with the black hole are rare, but the central parsecs are crowded with tens of thousands of stars, dense molecular clouds, and stellar remnants, all orbiting at breakneck velocities. Any object wandering too close would be shredded by tidal forces long before reaching the event horizon. The galaxy contains thousands of smaller black holes, remnants of massive stars that ended their lives in supernovae. Stellar mass black holes typically range from 5 to 20 solar masses, though some intermediate mass candidates reach hundreds of solar masses. Many of these are isolated, wandering through the disk or halo, and are detectable primarily via accretion-generated X-ray emissions observed by telescopes like Chandra or XMM Newton. Supernovae, the explosive deaths of massive stars, release energy on the order of 1044 joules, briefly outshining entire galaxies and ejecting matter into surrounding space. Shock waves can travel hundreds of light years, compressing nearby gas and dust, generating high-energy radiation and accelerating cosmic rays. Within the past 2 million years, several supernovae occurred within 300 light-years of Earth, forming structures such as the local bubble and influencing the flux of cosmic rays in the solar system. Neutron stars, the dense cores left after supernovae, have masses around 1.4 times that of the Sun, compressed into spheres about 20 kilometers across. With surface gravity billions of times stronger than Earth's, their magnetic fields can exceed 1 trillion Gauss, particularly in magnetars, producing bursts of gamma radiation. Some neutron stars spin hundreds of times per second, emitting focused beams of radiation as pulsars. The fastest known pulsar, PSR J1748-24446 AD, rotates at 716 times per second. Binary systems involve black holes or neutron stars orbiting companion stars, siphoning matter and forming accretion disks that emit X-rays and gamma rays. Cygnus X1, one of the first identified stellar mass black holes, resides about 6,000 light-years away in such a system. Material falling onto the black hole reaches temperatures of tens of millions of degrees Kelvin, emitting high-energy radiation. These systems are often hidden from optical view. Even ordinary stars can produce high-energy phenomena. Massive O and B-type stars generate stellar winds that eject material at thousands of kilometers per second, carving bubbles in the surrounding medium and creating turbulent, high-pressure regions. Clusters, like the Carina Nebula, home to Eta Carinae, demonstrate these stellar winds. Eta Carinae, over 100 times the Sun's mass, has experienced violent eruptions, propelling thousands of solar masses of material outward at hundreds of kilometers per second. The remnants of these events persist for millions of years as dense shells and high-energy regions. Rogue stars, ejected from clusters or due to galactic interactions, travel at unusual speeds, sometimes exceeding 1,000 kilometers per second. These hypervelocity stars often move toward the halo, or may escape the Milky Way entirely. Their paths are variable and not confined to the disk. Even interstellar debris such as stellar remnants, planetary bodies, and high-velocity gas clouds is present in the outer halo. The halo contains objects left over from mergers with dwarf galaxies, such as the Sagittarius dwarf elliptical galaxy. Streams of stars and gas from these events extend tens of thousands of light years, moving at speeds of several hundred kilometers per second. Radiation from stellar hazards is present throughout the galaxy. Gamma rays from supernovae, X-rays from accretion disks, and cosmic rays from shockwaves exist throughout the disk and halo. These high-energy particles can penetrate shielding and affect electronic systems. The central bulge contains fast-moving stars and the supermassive black hole. The disk includes binary systems, massive stars, molecular clouds, and hidden black holes. The halo contains globular clusters, rogue stars, and remnants of ancient galactic collisions. Radiation, shockwaves, and moving objects continually influence this environment. Even at great distances from the center, halo stars, neutron stars, and remnants of disrupted dwarf galaxies move at high velocities, influenced by the galaxy's mass and gravity. The Milky Way contains black holes, supernovae, neutron stars, stellar winds, rogue stars, and radiation hazards. These components create a high-energy environment throughout the galaxy. Light years and time, the scale problem. Even if one could survive the galaxy's hazards, dodge black holes, and thread a path through the interstellar medium, another obstacle emerges that is far less visible but no less insurmountable. The sheer scale of the Milky Way and the time required to traverse it. Distances in the galaxy are so vast that our familiar concepts of measurement and travel become almost meaningless. The Milky Way's diameter, estimated to be between 100,000 and 120,000 light-years, is a scale that dwarfs any human-built spacecraft or conceivable propulsion system. A light-year is the distance light travels in 1 year, nearly 9.46 trillion kilometers. Voyager 1, humanity's farthest traveled probe, has taken over 45 years to reach just 0.002 light-years from the Sunday. Traveling at 10% of the speed of light, a journey to the galactic edge would require more than 1 million years due to distance and velocity constraints. Stars move in complex orbits around the galactic center. The Sun orbits at roughly 220 kilometers per second, completing a revolution every 250 million years. Stars closer to the galactic core move at over 1,000 kilometers per second, while outer stars orbit more slowly, influenced by dark matter's gravitational pull. Distances in the Milky Way are affected by its thickness and structure. The stellar disk is about 1,000 light-years thick near the Sun, while the halo extends tens of thousands of light-years above and below the plane. The outer halo contains stars, globular clusters, and high-velocity clouds scattered unevenly. Distances between these objects are extremely large. Time dilation, predicted by Einstein's theory of relativity, affects high-speed travel. As an object approaches the speed of light, time slows relative to a stationary observer. While travelers moving near light speed experience less subjective time, the absolute distance across the galaxy remains unchanged. For example, a spacecraft traveling at 99% of light speed could cross the Milky Way in roughly 100,000 years of ship time, while millions of years would pass elsewhere. Communication signals would take tens of thousands of years to reach Earth or other locations. Cumulative hazards over time increase challenges for long-distance travel. Spacecraft would encounter radiation, cosmic rays, and dust collisions continuously over thousands of years. Equipment degradation, energy limitations, and biological lifespans further complicate sustained operations over these timescales. The galaxy's structure is uneven. Spiral arms, star clusters, and dense molecular clouds are irregularly spaced. The Perseus and Sagittarius arms contain massive star-forming regions and molecular clouds extending several hundred light-years in thickness. The halo and outskirts of the Milky Way contain globular clusters such as Omega Centauri and streams from dwarf galaxies like the Sagittarius dwarf elliptical galaxy. These objects move at hundreds of kilometers per second in irregular orbits. Even light requires tens of thousands of years to traverse the outer disk and halo. The nearest large neighboring galaxy, Andromeda, is 2.5 million light-years away. Technological limitations affect long-distance travel. Energy requirements for near-light-speed travel increase dramatically as velocity approaches the speed of light. Accelerating a massive spacecraft to 10% of light speed would require energy far beyond current production capabilities. Maintaining life support, radiation shielding, and structural integrity over thousands of years presents additional engineering challenges. Stellar evolution occurs over millions to billions of years. New stars form, old stars explode as supernovae, and the galaxy's structure changes over time. The Milky Way contains an estimated 400 billion stars, hundreds of millions of molecular clouds, and numerous rogue objects in the halo. It contains moving stars, dense regions, and distributed hazards. Even near light-speed travel would require millions of years, during which stellar positions and galactic structures would change. Dark matter and the invisible barrier. While distances, time, and stellar hazards create obvious barriers within the Milky Way, an invisible and far more pervasive obstacle underlies the entire galaxy: dark matter. Unlike stars or gas clouds, dark matter does not emit, reflect, or absorb light, rendering it entirely undetectable by traditional observation. Yet its presence is undeniable, inferred from the motions of stars, globular clusters, and satellite galaxies, as well as from gravitational lensing that bends light from distant galaxies. Dark matter constitutes the majority of the Milky Way's mass, forming an invisible gravitational skeleton that holds the galaxy together and imposes insurmountable limits on travel to its edge. The earliest hints of dark matter in the Milky Way came from studies of galactic rotation curves in the 1970s. Astronomers such as Vera Rubin observed that stars in the outer disk orbit the galactic center at speeds far higher than predicted by visible mass alone. For example, stars located 50,000 light-years from the center maintain orbital velocities around 220 kilometers per second, roughly the same as stars located near the Sun at 8,000 light-years. If only luminous matter were present, these stars would be moving far too fast and should escape the galaxy. This discrepancy necessitates a massive, invisible halo extending well beyond the visible disk. Current estimates suggest that dark matter comprises roughly 85–90% of the Milky Way's total mass, with the visible stars, gas, and dust accounting for the remainder. The galaxy's total mass, therefore, reaches approximately 1.5 trillion solar masses, far larger than what can be seen. The dark matter halo stretches at least 150,000 to 200,000 light-years from the galactic center and may extend even farther. It is roughly spherical, although cosmological simulations suggest it may be slightly flattened along the disk plane. Density decreases gradually with distance from the center, but even in the outer halo, dark matter dominates the gravitational potential. Within this halo, smaller concentrations, known as subhalos, add another layer of complexity. These subhalos, with masses ranging from 1 million to 1 billion solar masses, are remnants of the galaxy's formation and mergers with dwarf galaxies. Their gravitational effects are evident in perturbations of stellar streams and tidal debris. The Sagittarius stream, a trail of stars stripped from the Sagittarius dwarf elliptical galaxy, exhibits gaps and bends consistent with encounters with dark subhalos. dark matter plays a critical role in maintaining the Milky Way's spiral arms. Spiral density waves, which compress gas and trigger star formation, are stabilized by the gravitational potential of the dark halo. Without dark matter, the disk would not rotate as it does. Stars in the outer arms would drift away and the spiral pattern would dissipate. Even at the outermost regions, dark matter continues to dominate. The Milky Way is part of the local group, and the gravitational influence of dark matter extends beyond the disk to encompass satellite galaxies such as the Large and Small Magellanic Clouds. These dwarf galaxies, orbiting tens of thousands of light-years away, are bound by the galaxy's dark matter halo. Streams of stars and gas stripped from these satellites, often spanning hundreds of light-years, trace the contours of dark matter substructures. Cosmological simulations indicate that dark matter may have clumpy substructure even at smaller scales. Dense clumps or filaments within the halo could create localized enhancements in gravitational force, subtly altering trajectories over vast distances. While these substructures are not yet directly observed, their predicted presence indicates that even seemingly empty regions could contain invisible concentrations affecting motion of objects. Dark matter's influence extends to stellar streams, globular clusters, and high-velocity stars. Globular clusters, like Omega Centauri, located roughly 15,800 light-years from the galactic center, move under the combined gravitational influence of visible stars and dark matter. High-velocity stars, reaching speeds over 1,000 kilometers per second, are also constrained by the halo's gravity. Dark matter affects the evolution of the galaxy over cosmological timescales. As the Milky Way interacts with satellite galaxies, the halo absorbs energy and momentum, altering the orbits of stars and clusters. The galaxy's projected merger with Andromeda, in roughly 4 billion years, will involve the interaction of visible matter and overlapping dark matter halos. The dark matter halo extends at least 200,000 light-years from the galactic center, and its gravitational pull remains significant throughout this volume. The escape velocity in these regions is roughly 500 kilometers per second. The Milky Way gradually transitions into intergalactic space, with gravitational influence extending over hundreds of thousands of light-years. Beyond gravitational effects, dark matter is critical to understanding the galaxy's formation history. The Milky Way formed through mergers and accretions of smaller galaxies over billions of years. Dark matter provided the framework within which visible matter coalesced into stars, clusters, and spiral arms. Tidal streams, such as those from the Sagittarius and Canis Major dwarf galaxies, provide observational evidence of this process. Dark matter cannot be observed directly, and its gravitational influence affects motion throughout the galaxy. Its presence creates perturbations that alter trajectories and velocities of stars and other objects over large distances and long timescales. The Milky Way's dark matter halo extends far beyond the visible disk and dominates the motions of stars, gas, and clusters. Subhalos and smaller clumps create perturbations that influence stellar streams, satellite galaxies, and high-velocity stars, affecting their paths throughout the galaxy. Intergalactic space, where the Milky Way ends. Beyond the dark matter halo, past the outermost stars and globular clusters, the Milky Way gradually transitions into the vast emptiness of intergalactic space. Yet this edge is not a sharp boundary, a wall to cross, or a place where the galaxy suddenly stops. Instead, the transition is a diffuse, sprawling frontier where the influence of the Milky Way's gravity slowly diminishes and the intergalactic medium begins to dominate. Understanding this region is essential to grasp why reaching the edge of the galaxy is not only a matter of distance, but also of context. What appears to be empty space is shaped by forces and structures extending far beyond the visible galaxy. The first signs that the Milky Way extends beyond sparse stars come from studies of satellite galaxies and stellar streams. The Large and Small Magellanic Clouds, orbiting roughly 160,000 and 200,000 light-years from the galactic center, are bound to the Milky Way by gravity and surrounded by their own dark matter halos. Streams of stars and gas, such as the Magellanic Stream, extend hundreds of thousands of light-years through the galactic halo. The intergalactic medium is incredibly tenuous but present throughout space. Composed mostly of hydrogen and helium with trace amounts of heavier elements, its density averages around 1 atom per cubic meter. In comparison, the densest molecular clouds in the Milky Way's disk can contain billions of atoms per cubic centimeter. Gas slowly accretes onto the galaxy, feeding star formation and replenishing material lost to supernova-driven winds. Globular clusters in the halo mark the outer limits of the galaxy's influence. Some, like NGC 2419, are nearly 300,000 light-years from the galactic center. These clusters move in elliptical orbits shaped by both visible and dark matter, showing that the Milky Way's pull extends far beyond the disk and spiral arms. Stars migrate due to tidal interactions with satellite galaxies, gravitational perturbations from dark matter subhalos, and the long-term evolution of the halo. Rogue dwarf galaxies in the local group include Leo I and Leo II, which orbit the Milky Way at distances between 800,000 and 1.2 million light-years. Their paths are governed by the combined gravitational pull of the Milky Way, Andromeda, and other nearby masses. The distribution of dark matter continues to influence the outskirts. Although the density of the halo decreases with distance, its gravitational effect persists well beyond the visible stars. The escape velocity at the outermost halo, around 200,000 light-years, remains roughly 500 kilometers per second, keeping many stars and satellite galaxies bound. Observations of the local group, containing the Milky Way, Andromeda, and roughly 50 other galaxies, provide context. Andromeda lies about 2.5 million light-years away and is on a collision course with the Milky Way. The gravitational interplay of these galaxies, along with smaller companions like M33 and the Triangulum galaxy, affects the movement of stars and gas in the Milky Way's far halo. The intergalactic medium is not entirely empty. It contains tenuous clouds of ionized gas, sometimes stretching millions of light-years. These clouds, part of the so-called warm-hot intergalactic medium, are heated to temperatures of 100,000 to 10 million Kelvin by shock waves from galaxy formation and collisions. High-energy particles and radiation are present in this environment, and the density is far lower than in the interstellar medium. Even light takes thousands of years to cross these outer zones. For example, light from distant globular clusters in the halo takes hundreds of thousands of years to reach the inner galaxy. Navigation in this region is influenced by the low density of visible objects and the gravitational effects of dark matter and satellite galaxies, which shift positions over millions of years. Tidal forces from satellite galaxies also shape the outer regions. The Sagittarius dwarf elliptical galaxy, currently being absorbed by the Milky Way, creates long streams of stars stretching over 100,000 light-years. These streams indicate that matter in the outer halo is actively rearranged and the region undergoes ongoing accretion. The Milky Way's magnetic field extends into the halo and beyond, influencing cosmic rays and charged particles in intergalactic space. While weaker than in the disk, these fields guide particle motion. Cosmic rays in these regions, though sparse, travel at nearly the speed of light, interacting with matter over millions of years. Tenuous gas, dark matter influence, and moving stellar streams are present in the outer halo. Intergalactic space is a continuum where the Milky Way gradually transitions into the local group. The galaxy's outskirts contain sparse stars, tidal streams, satellite galaxies, dark matter, and intergalactic medium, all of which interact over millions of years. The concept of an edge in intergalactic terms is gradual. There is no sudden drop-off where the Milky Way ends. The galaxy transitions into a region dominated by the sparse matter of the local group. Stars become fewer, radiation fields weaken, and the influence of the galaxy's dark matter halo diminishes over distance. Even beyond the halo, the Milky Way's influence extends indirectly. Interactions with Andromeda and other local group members will alter the galaxy over billions of years. Tidal streams from absorbed dwarf galaxies continue to trace gravitational contours. Sparse stars, tenuous gas, satellite galaxies, and dark matter dominate the outer regions of the Milky Way. Gravitational fields, tidal streams, and low-density material extend across these areas, influencing motion over millions of years. Voyagers and probes. Lessons from spacecraft. While contemplating the Milky Way's vast distances and invisible barriers, it is natural to look for examples of human exploration that hint at what it might take to traverse the galaxy. The farthest objects humanity has ever sent into space are our robotic spacecraft, most notably Voyager 1 and Voyager 2, launched in 1977. These probes were designed to study the outer planets of the solar system, but they have since become our first ambassadors to interstellar space. Tracking their journeys provides a sobering perspective on the impossibility of reaching the edge of the Milky Way. Voyager 1 is currently the most distant human-made object, traveling at about 17 kilometers per second relative to the Sun, or roughly 61,000 kilometers per hour. It has taken over 45 years to reach just beyond the heliosphere, the bubble of charged particles and magnetic fields surrounding the Sunday. This places Voyager 1 about 23.3 billion kilometers from the Sun, or roughly 0.0025 light years. The Milky Way's visible disk has a radius of roughly 50,000 light years. Voyager 2, moving at a slightly slower 15 kilometers per second, is currently closer to the Sun than Voyager 1. Both Voyagers were powered by radioisotope thermoelectric generators, which convert heat from decaying plutonium-238 into electricity. The spacecraft are now operating at a fraction of their original capacity. Instruments have been turned off over the decades to conserve power, and communication with Earth requires sensitive antennae like those of NASA's Deep Space Network. The Pioneer 10 and 11 missions offer additional perspective. Launched in the early 1970s, they were the first spacecraft to traverse the asteroid belt and leave the inner solar system. Pioneer 10, traveling at about 12 kilometers per second, is now over 120 astronomical units from the Sun, which is still only a tiny fraction of 1 light year. The trajectories of these spacecraft also demonstrate the effects of gravitational assistance. Both Voyagers used gravity assists from planets like Jupiter and Saturn to accelerate. Gravity assists work well within the solar system because planets provide concentrated mass and predictable orbits, but on galactic scales, stars are too distant and moving too fast relative to each other to provide practical propulsion. Interstellar space lacks the kind of easily exploitable energy sources available in our planetary neighborhood. Signals from Voyager 1 take over 21 hours to reach Earth at the speed of light, traveling over 23 billion kilometers. Communication delays increase with distance due to the finite speed of light. Cosmic rays, solar wind, and micrometeoroid impacts pose threats, and over decades, these forces gradually degrade spacecraft materials. Radiation exposure in interstellar space is higher than within the protective heliosphere, and even small amounts of dust traveling at tens of kilometers per second can puncture or erode shielding. Voyager data also reveal the nature of the medium beyond our solar system. The heliopause, where solar wind meets the interstellar medium, is a turbulent and tenuous boundary. Beyond it lies a region filled with low-density gas, cosmic rays, and magnetic fields that vary across light years. While this environment is sparse compared to the inner solar system, it is not empty. For an object moving at high speed, even collisions with 1 atom per cubic centimeter can have measurable effects over millions of years. The interstellar medium, invisible yet omnipresent, introduces drag, erosion, and radiation hazards that increase with both distance and duration of travel. Other probes, like New Horizons, launched in 2006 and famous for its flyby of Pluto, have traveled at roughly 16 kilometers per second. New Horizons is still confined to the outer reaches of the Kuiper Belt, less than 0.0005 light-years from Earth. The Milky Way's diameter is tens of thousands of times larger than these distances. Maintaining a functional probe across decades required careful redundancy, reliable systems, and remote command capabilities. The golden records onboard Voyager 1 and 2 contain sounds, images, and messages representing humanity, intended for any extraterrestrial civilization that might encounter the spacecraft. Hypothetical propulsion advances, such as fusion or antimatter engines, could increase spacecraft speed. Accelerating a spacecraft to 10% of the speed of light would reduce travel times, but the journey to the nearest edge of the galaxy would still take over 500,000 years. Radiation, material fatigue, life support, and cosmic hazards remain significant challenges over such durations. Voyager and other probes have traveled only a tiny fraction of a light year. They encounter radiation, dust, and interstellar gas, and communication is limited by the speed of light. Energy, time, and durability constraints affect long-duration missions. Robotic spacecraft take decades to reach regions that are tiny fractions of the Milky Way's diameter. Hazards include radiation, dust, and interstellar gas. Distances and time impose limitations on spacecraft travel across the galaxy. The limits of technology, why engines can't overcome galactic scales. After examining the achievements of the Voyagers and other spacecraft, it becomes clear that one of the biggest barriers to reaching the edge of the Milky Way is technology itself. Propulsion systems, energy storage, material science, and even navigation, all the components required for interstellar travel, face limitations that grow exponentially with distance. The galaxy is not simply a larger version of the solar system. Its vast scale transforms familiar engineering problems into near insurmountable challenges. To understand why reaching the edge is impossible, it is essential to explore these technological constraints in detail. The first challenge is propulsion. Chemical rockets, which powered missions from Sputnik to Voyager, are completely inadequate for galactic travel. Even the most advanced chemical boosters, like NASA's Space Launch System, can achieve escape velocities from Earth on the order of 11 kilometers per second. Yet crossing the Milky Way, even at the distance of the Sun, from the center about 26,000 light-years, would require speeds approaching a significant fraction of the speed of light. Hypothetical nuclear, thermal, or ion drives can offer higher efficiency. The Dawn spacecraft, powered by ion propulsion, achieved a top velocity of about 10 kilometers per second relative to Earth. While impressive for solar system missions, it would take tens of millions of years to reach the outer regions of the galaxy. Even if a fusion engine like the one conceptualized in Project Daedalus could theoretically reach 12% of the speed of light, it would still require hundreds of thousands of years to traverse a galactic radius. Energy storage and generation present an equally severe constraint. Voyager 1 and 2 survive on the decay of plutonium-238, producing only a few hundred watts of electrical power after decades. Scaling this up to a starship capable of sustaining propulsion, life support, and shielding for thousands of years multiplies energy requirements by orders of magnitude. Fusion-based propulsion would require enormous fuel reserves and continuous maintenance of extremely high temperatures and magnetic confinement over centuries or millennia. For antimatter propulsion, containment of even a gram of antimatter presents engineering risks. Accidental contact with normal matter would result in explosive annihilation. Material limitations further complicate the picture. Spacecraft traveling through the Milky Way at significant fractions of the speed of light would encounter interstellar particles at velocities that amplify their destructive potential. Even hydrogen atoms, the most abundant particles in space, could impact surfaces with tremendous kinetic energy at near light speeds, effectively vaporizing unshielded materials. For example, a particle with the mass of 1 proton traveling at 1 has an energy equivalent to several thousand electron volts, enough to erode hull surfaces over decades. Current spacecraft shielding, such as titanium or aluminum, is insufficient for these conditions. Concepts like Whipple shields or magnetic deflectors exist in theory, but scaling them to protect a vessel for tens of thousands of light years presents engineering demands beyond current capabilities. Maintaining air, water, food, and waste systems for extended periods presents severe technological challenges. Closed-loop ecological systems, studied on Earth in experiments like BIOS, 3 or the International Space Station, have only been sustainable for months or a few years. Robotic missions like the Voyagers avoid life support entirely, but still face energy and environmental limitations. Navigation presents another major barrier. Within the solar system, spacecraft can rely on the predictable positions of planets and the Sun for gravity assists and trajectory corrections. Beyond the solar system, stars are moving relative to each other at hundreds of kilometers per second. A vessel attempting to reach the outer edge of the galaxy would need to account for the motion of tens of billions of stars, each altering gravitational pathways subtly over thousands of years. Even small errors in trajectory would accumulate, resulting in deviations of thousands of light years over the course of a journey. Unlike in planetary navigation, there is no fixed reference point in the galactic environment that can be relied upon for course correction across millennia. Signals sent at the speed of light take years to traverse even nearby stars. For example, a message to Proxima Centauri, 4.24 light-years away, takes over 4 years to arrive. Across the 50,000 light-year radius of the Milky Way, messages would take tens of thousands of years. Autonomous systems would need to operate continuously over millennia, a scenario without precedent in human engineering. Software and mechanical components degrade over decades, complicating long-term operation. Heat dissipation and thermal management also pose obstacles rarely encountered in small-scale missions. Engines producing continuous high thrust generate enormous heat, which must be radiated away. In the vacuum of space, heat cannot be convected or conducted to a surrounding medium, leaving only radiation. Large radiators would need to dissipate gigawatts of energy over centuries without degradation. Failure to manage heat could compromise propulsion, life support, or structural integrity. In comparison, Voyager spacecraft manage mere hundreds of watts, orders of magnitude smaller than a galactic-scale vessel would require. Radiation hazards remain a persistent issue. The Milky Way is permeated with cosmic rays, gamma-ray bursts, and energetic particles accelerated by supernovae. A spacecraft traveling thousands of light-years would be exposed continuously, and shielding to protect humans or sensitive electronics at relativistic speeds becomes increasingly difficult. For example, Voyager's instruments degrade slowly due to cosmic radiation, but a starship traveling at 1c would be impacted by every interstellar particle at far higher energies, dramatically increasing radiation exposure. Long-term material fatigue from this radiation would further compromise structural and electronic systems over millennia. All fuel, repair materials, and energy must be carried on board, as opportunities to refuel or resupply are non-existent. Harvesting interstellar hydrogen for fusion, a concept in Bussard ramjet designs, faces challenges of collection efficiency and drag that likely outweigh benefits. A journey spanning tens of thousands of light-years would require full onboard provisioning for all resources. Technological constraints, including propulsion, energy, heat management, radiation shielding, navigation, and life support, scale with galactic distances. Current robotic missions, like the Voyagers, operate successfully only within the solar system, highlighting the increasing demands on technology for interstellar travel. Current technology does not allow a spacecraft, robotic or crewed, to traverse tens of thousands of light-years within practical timeframes. Engineering challenges, including propulsion, energy supply, shielding, navigation, and life support, increase with distance and duration, requiring capabilities far beyond present human technology. The warp dream, hypothetical, faster-than-light travel. When confronted with the immense scale of the Milky Way, human imagination naturally turns to possibilities that defy conventional physics. The distances, involved tens of thousands of light-years across the galactic disk, render even the fastest spacecraft completely inadequate. This limitation has inspired decades of theoretical research into faster-than-light travel, from warp drives to wormholes, as a potential way to bridge cosmic distances in a manageable timeframe. These ideas capture the imagination because they promise to shrink the galaxy to human scales, but a closer examination reveals immense physical, technological, and energy constraints that make the dream currently impossible. The most widely discussed concept is the Alcubierre warp drive, first proposed in 1994 by physicist Miguel Alcubierre. Instead of accelerating a spacecraft through space, the ship remains in a bubble of space-time, while space itself contracts in front of it and expands behind it. In theory, this allows the bubble to move faster than light relative to distant observers, while the ship inside experiences no acceleration. Initial calculations suggested that a warp bubble would require negative energy equivalent to the mass of the observable universe. Later refinements reduced this to the mass energy of Jupiter, or a small star, still far beyond human engineering capabilities. Creating or manipulating such energy would require levels of control over matter and space-time that are completely theoretical. Negative energy itself remains a speculative concept. Certain quantum effects, such as the Casimir effect, demonstrate that negative energy density can exist in small, controlled laboratory conditions. But these effects are minuscule and cannot be scaled to the vast amounts required for a warp bubble. Even if sufficient negative energy could be produced, it would need to be stabilized and shaped precisely a level of precision far beyond current or foreseeable technology. Any miscalculation could collapse the bubble, destroying the spacecraft. Warp drives are theoretically compatible with Einstein's equations, but currently outside experimental feasibility. Wormholes, another faster-than-light concept, offer a complementary perspective. Einstein and Rosen proposed bridges through space-time in 1935, now called Einstein-Rosen bridges. If traversable, these tunnels could connect two distant points in the Milky Way instantaneously. Hypothetically, a spacecraft entering one end could exit tens of thousands of light-years away without ever traveling faster than light locally. Yet traversable wormholes introduce extraordinary challenges. They require exotic matter to keep the throat of the wormhole open, which must have negative energy density to counteract gravitational collapse. Laboratory observations suggest that only quantum-scale amounts exist, insufficient for macroscopic structures large enough to carry a spacecraft. Furthermore, wormholes are inherently unstable. The passage of any particle, photon, or cosmic ray could destabilize the structure, making safe travel practically impossible. Even if these obstacles were overcome, the galaxy itself, poses enormous hazards to faster-than-light travel. The Milky Way is far from empty. Stars, planetary systems, dust clouds, and black holes are scattered throughout the disk and halo. At relativistic speeds, collisions with even a single hydrogen atom can release destructive energies. Traveling at 10% the speed of light, a proton encountered head-on carries the kinetic energy of a cannonball striking a wall. Shielding a spacecraft to survive continuous exposure to such impacts would require massive layers of material or intense magnetic fields, which themselves demand energy and add weight. Accelerating to higher fractions of light speed exponentially increases the energy of every collision, making traversal of even relatively sparse regions of space hazardous. Radiation presents a parallel danger. Cosmic rays, gamma-ray bursts, and X-ray emissions permeate the Milky Way. At relativistic speeds, the apparent energy of these particles is dramatically increased, intensifying their destructive potential. Voyager spacecraft, moving slowly by comparison, experience minor radiation effects over decades. A near-light-speed ship would accumulate lethal doses of radiation from interstellar particles in a matter of years or centuries. Shielding and navigation would need to account for dense regions of radiation. Energy requirements for hypothetical FTL travel are staggering. Even optimistic warp drive calculations demand energy on scales comparable to entire planets. To cross the Milky Way's 100,000 light-year diameter, maintaining a warp bubble for thousands of years, or even a single voyage across a few thousand light-years, would consume energy far beyond anything humanity has harnessed. Fusion, antimatter, or zero-point energy might, in principle, provide enormous power, but all face fundamental engineering and physics challenges. Antimatter containment, for example, is precarious. Even micrograms coming into contact with normal matter produce explosive annihilation. Fusion, while powerful, requires sustained conditions that no spacecraft has maintained beyond seconds. Scaling energy production to galactic distances would require energy levels far beyond current capabilities. Navigation presents another challenge. The Milky Way is dynamic. Stars move at hundreds of kilometers per second, spiral arms rotate, and satellite galaxies weave through the halo. A faster-than-light ship cannot rely on fixed maps. The destination itself may shift during transit, and even small deviations at relativistic speeds could lead to collisions. Unlike planetary navigation, where gravity assists and predictable orbits can be exploited, galactic-scale navigation requires autonomous systems capable of adjusting to long-term stellar motions. Hypothetical alternatives, like Krasnikov tubes, propose creating a tunnel through space-time that allows superluminal travel in one direction, but the path must be pre-built by a spacecraft moving at subluminal speeds. The size of the Milky Way means that such preparation would take millions of years, and any traveler attempting to use a tube would arrive only after infrastructure spanning tens of thousands of light-years had been constructed. Even ignoring physics, environmental factors remain a hurdle. Dust, rogue planets, stellar remnants, and black holes populate the Milky Way. Traveling through the galaxy at any extreme speed risks catastrophic encounters. The interstellar medium itself, though sparse, contains gas clouds and ionized particles. Over tens of thousands of light-years, these can interact with a high-speed vessel to produce erosion, electrical charging, and radiation hazards. Finally, cosmological limits impose theoretical constraints. Superluminal travel can produce causality paradoxes, potentially allowing effects to precede causes. Certain solutions in general relativity might permit loopholes, but they require precise control over space-time geometry, energy distributions, and exotic matter. Concepts like warp drives, wormholes, and Krasnikov tubes present theoretical methods for faster-than-light travel, but each requires energy, stability, navigation, and radiation management at levels currently beyond technological capability. Even with speculative engineering and theoretical breakthroughs, the Milky Way contains dynamic hazards, moving stars, and forces such as dark matter. Any faster-than-light travel would require navigating these factors over tens of thousands of light-years, presenting challenges far beyond current technological capability. Time dilation and relativity, the cosmic speed trap. Having explored the limits of conventional propulsion and the tantalizing ideas of faster-than-light travel, it becomes clear that even reaching near-light speeds introduces a completely different set of barriers. The consequences of Einstein's theory of relativity, time dilation, length contraction, and the cosmic speed limit are not just theoretical curiosities. They impose fundamental constraints on how a spacecraft could traverse the Milky Way. These effects transform the galaxy from a challenging destination into an essentially unreachable frontier for any crewed mission or even robotic expedition traveling at relativistic speeds. Time dilation, as predicted by special relativity, means that time experienced by a traveler moving close to the speed of light passes differently than for those remaining at rest relative to Earth. For instance, if a spacecraft were to travel at 90% of light speed, a journey of 1,000 light-years as measured from Earth would take just over 1,111 years from the perspective of the stationary observer. For the traveler, however, due to time dilation, the trip would seem to last only about 460 years. At speeds approaching 99% of light speed, a trip to the outer regions of the Milky Way, approximately 50,000 light-years away, would take decades of subjective time for the travelers and tens of thousands of years from an Earth-bound perspective. Communication or coordination with Earth would be subject to these time differences. Time dilation also intersects with technological limitations. Spacecraft traveling near light speed would face relativistic effects on mass, requiring exponentially more energy to accelerate even slightly faster. This relativistic mass increase is a direct consequence of Einstein's formula, which dictates that as velocity approaches the speed of light, the energy required to continue accelerating rises toward infinity. Achieving velocities near 99% of light speed would require energy levels far exceeding the output of current or proposed propulsion systems, including fusion or antimatter engines. The hazards of traveling at such velocities are significant. The interstellar medium, while extremely tenuous, produces collisions at relativistic speeds, with energies capable of vaporizing hull materials or penetrating protective shielding. At 99% of light speed, even a single dust particle encountered head-on would impact with energy equivalent to several kilograms of TNT. Over thousands of light-years, cumulative collisions with these particles would have substantial effects on the spacecraft, regardless of shielding sophistication. Relativity also imposes constraints on navigation and observation. Due to the phenomenon of length contraction, the distances in the direction of travel appear compressed for the traveler, while the perpendicular dimensions remain unchanged. For a journey of tens of thousands of light-years, the galaxy would appear flattened in the direction of motion, but hazards such as black holes, neutron stars, and supernova remnants would still be encountered. Any course deviation could result in collisions. Moreover, the Doppler effect becomes extreme at these speeds. Light from stars ahead of the ship shifts into high-energy gamma rays, while light from behind is redshifted to longer wavelengths. Advanced shielding would be required to protect against particles and electromagnetic radiation. Time dilation affects mission planning. Even at 99.9% of light speed, the subjective time experienced by travelers could be decades or centuries, while Earth-based observers would measure tens of thousands of years passing. Planning for resupply, repair, or colonization would be complicated by this divergence between local and Earth time. The effects of general relativity affect travel near massive objects. The Milky Way contains regions of intense gravity, from stellar mass black holes to the supermassive black hole Sagittarius A star at the center. Traveling near these regions introduces gravitational time dilation, where time passes more slowly for those closer to the mass relative to distant observers. Navigating such areas at relativistic speeds requires precise calculations of local spacetime curvature. Minor miscalculations could result in deviations from the intended trajectory. Another factor is the limitation on acceleration. Continuous acceleration at high speeds introduces practical and physiological challenges. Even a modest acceleration of 1 g, the force of Earth's gravity applied continuously for months, would allow relativistic speeds to be approached. Maintaining life support, structural integrity, and energy supply under constant acceleration for years or decades would require extremely advanced engineering. Crew members would age at normal rates relative to the ship, while much longer time passes for observers outside the vessel. Communication delays occur at relativistic velocities. If a ship traveling at 99% of light speed sends a message to Earth, the time for signals to arrive and for replies to return could extend to thousands or tens of thousands of years. Coordination or guidance from Earth would be delayed by these time intervals, limiting real-time control. Even robotic missions are subject to relativistic constraints. A probe traveling at 90% of light speed would reduce travel time to subjective decades, but energy requirements, particle collisions, and radiation exposure are all increased. Voyager-class probes, moving at tens of kilometers per second, experience minor erosion over decades. A relativistic probe would encounter thousands of times the energy impacts from interstellar particles over a shorter subjective period. Advanced shielding or electromagnetic deflection systems would be necessary, increasing mass and energy demands for the mission. Even hypothetically combining warp drive concepts with relativistic travel does not eliminate relativistic constraints. Energy, shielding, and navigation challenges remain, and time dilation affects interactions with distant locations. While warp bubbles might allow faster-than-light travel in principle, practical limitations of energy, exotic matter, and relativistic hazards remain significant. Time dilation and relativistic effects impose constraints on interstellar travel. At near light speeds, distance, energy requirements, particle hazards, radiation, and communication challenges all scale with velocity. Travelers experience shorter subjective time, while external reference points age over thousands of years. These effects complicate navigation, collision avoidance, and energy management, and must be accounted for in mission design according to the laws of physics, radiation, cosmic rays, and galactic hazards. After examining the fundamental limits imposed by relativity, it becomes clear that even if a spacecraft could somehow approach the speed of light, the Milky Way itself presents a deadly gauntlet of radiation and energetic hazards. Unlike the solar system, where magnetic fields and planetary atmospheres provide substantial protection, the interstellar medium is a harsh environment. Cosmic rays, gamma-ray bursts, stellar winds, and supernova remnants bombard any object traveling through space, creating dangers that increase dramatically with speed and distance. For human travelers, the risks are immediate and lethal, while even robotic probes face material degradation and operational failure over long journeys. Cosmic rays are among the most pervasive threats. These high-energy particles originate from sources such as supernovae, pulsars, and active galactic nuclei, traveling at near-light speeds across the galaxy. Composed mostly of protons, with a small fraction of heavier nuclei and electrons, cosmic rays carry tremendous energy. The typical cosmic ray particle striking the solar system carries between 1 and 10 giga-electron volts, though rare ultra-high-energy cosmic rays can reach energies exceeding 10-20 electron volts. To put this in perspective, a single ultra-high-energy proton striking a spacecraft at relativistic speeds would deliver energy equivalent to several kilograms of TNT concentrated on a minuscule point, enough to vaporize small sections of hull material. For a vessel attempting to traverse the Milky Way, such impacts would be unavoidable. Gamma-ray bursts represent another catastrophic hazard. These brief, intense explosions, originating from massive star collapses or neutron star mergers, release more energy in seconds than the Sun emits in its entire lifetime. Observations by the Swift and Fermi satellites suggest that gamma-ray bursts occur approximately once per million years in the Milky Way, though even a single exposure within a few thousand light-years could sterilize the surface of a spacecraft or disable electronics beyond repair. Unlike cosmic rays, which are relatively constant, gamma-ray bursts are unpredictable, leaving no opportunity for avoidance except by chance. Supernova remnants are scattered throughout the galaxy, particularly along the spiral arms. The Milky Way has an estimated 2 to 3 supernovae per century, and each event produces shockwaves of high-energy particles and radiation expanding at thousands of kilometers per second. A spacecraft passing through a supernova remnant would face intense fluxes of X-rays, gamma rays, and energetic ions. Even thick shielding would be challenged, as prolonged exposure over tens of thousands of light-years adds cumulative damage that can degrade metals, electronics, and composite materials. Stellar winds, emitted from massive stars, also produce hazards over galactic distances. While less immediately destructive than supernovae or gamma-ray bursts, these streams of charged particles, protons, electrons, and heavier ions flow at hundreds to thousands of kilometers per second. Over millennia of travel, cumulative bombardment can erode unprotected hull surfaces, charge electronic components, and increase background radiation inside the ship. Wolf-Rayet stars, known for their exceptionally strong winds, can produce local particle fluxes thousands of times higher than the average interstellar medium, creating dangerous hot zones in the galaxy. Interstellar dust, although sparse, presents significant risks at high speeds. A spacecraft moving at even 1 C will encounter tiny grains of silicate or carbonaceous dust with enormous relative energy. Each collision, though with a particle only a fraction of a millimeter across, would generate micro-explosions capable of eroding the surface and damaging sensitive instruments. Over tens of thousands of light-years, these effects accumulate, potentially compromising hull integrity and onboard systems. Robotic probes may survive longer than humans, but even instruments with radiation-hardened electronics would eventually fail without maintenance. Radiation hazards also interact with human biology in severe ways. Galactic cosmic rays penetrate spacecraft shielding, causing DNA damage, increasing cancer risks, and producing neurocognitive effects. Studies using the NASA Space Radiation Laboratory have demonstrated that exposure to heavy ions, like iron nuclei, which are common in cosmic rays, can induce complex cellular damage in animal models. Unlike low Earth orbit, where the magnetosphere provides substantial protection, interstellar travel offers no such shielding. Astronauts traveling for decades would face cumulative doses far exceeding current lifetime limits, making prolonged habitation impossible without breakthroughs in artificial shielding or medical countermeasures. Magnetic fields of the galaxy provide only minimal protection against high-energy particles. While the Sun's heliosphere deflects lower-energy cosmic rays from reaching the inner solar system beyond its reach, the interstellar magnetic field is weak and patchy. At speeds approaching a significant fraction of light speed, even these weak fields become ineffective. Charged particles collide with the spacecraft at relativistic energies, regardless of field orientation. The galaxy, therefore, is a relentless radiation environment, where every trajectory carries exposure risks that scale with both distance and velocity. Neutron stars and black holes are another class of hazards that cannot be ignored. Neutron stars emit intense beams of X-rays and gamma rays along their magnetic poles, creating zones of extreme radiation that extend for light years. Pulsars, rotating hundreds of times per second, generate particle winds capable of stripping away material from any unshielded vessel. Black holes, particularly the supermassive one at the galactic center, distort space-time and accelerate nearby matter to relativistic velocities, producing high-energy jets. While direct collisions with these objects are rare, the extended influence of their radiation fields and gravitational effects make certain regions effectively impassable. Even interstellar gas clouds, primarily composed of hydrogen, create risks at high velocity. Although their densities are low, typically a few hundred atoms per cubic centimeter, relativistic collisions transform these seemingly empty clouds into lethal obstacles. At 0 5C, a single hydrogen atom carries kinetic energy equivalent to a fast-moving projectile. Crossing a molecular cloud, several light years thick, would result in continuous bombardment of the spacecraft, gradually eroding materials and potentially penetrating internal compartments. Over the span of a galactic journey, encountering multiple clouds is unavoidable. The combined effects of these hazards create multiple overlapping risks for interstellar travel. Radiation, cosmic rays, dust, and energetic particles interact, accumulate, and compound over distance. A spacecraft could encounter a supernova remnant, a dense molecular cloud, and a high-energy particle storm from a nearby pulsar sequentially along a path, producing energy levels that exceed the protection provided by current shielding. Even advanced theoretical technologies, such as energy fields or superconducting hulls, have not been tested under these conditions. The Milky Way is a dynamic, three-dimensional environment containing radiation, particles, stellar remnants, and energetic hazards. Cosmic rays, gamma-ray bursts, supernova remnants, magnetic fields, and interstellar dust present continuous exposure risks over galactic distances. At relativistic speeds, the energy of particle collisions and radiation exposure increases. Current technologies are insufficient to fully protect human travelers, and robotic probes experience material degradation over long durations. Radiation, cosmic rays, and galactic hazards impose significant constraints on interstellar travel. Effective protection would require propulsion capable of relativistic speeds, as well as advanced materials, energy sources, and shielding systems beyond current capabilities. The combination of vast distances and energetic hazards presents practical challenges that current technology cannot overcome. The ever-moving target, galactic evolution. By the time a spacecraft, theoretical or otherwise, confronts the radiation and particle hazards of interstellar space, a new, subtler challenge emerges. The Milky Way is not a static structure. Stars orbit, spiral arms rotate, clusters drift, and gas clouds shift over thousands to millions of years. The edge of the galaxy is not a fixed boundary. It is a moving target shaped by dynamic processes that have been ongoing for billions of years. Any attempt to reach the edge must contend not only with distance, energy, and hazards, but with the galaxy itself evolving during the journey, making the destination a constantly shifting, sometimes vanishing, goal. Galactic rotation is the primary driver of motion on large scales. Stars orbit the galactic center at speeds ranging from 200 to 250 kilometers per second, depending on their distance from the core. Our Sun, located approximately 27,000 light-years from Sagittarius A star, completes an orbit roughly every 225–250 million years. Spiral arms themselves are density waves, not solid structures, so as stars move, the arms appear to sweep past them. This means that a spacecraft aiming for a particular segment of a spiral arm would find that the target has shifted by tens of thousands of light years over millennia. Regions of interest, such as the Perseus arm or the Sagittarius arm, are constantly changing their relative positions to any traveller, rendering fixed coordinates nearly meaningless over interstellar timescales. Stellar motion is another complicating factor. Individual stars exhibit proper motion movement relative to the local standard of rest. Nearby stars, like Barnard's star, move at extraordinary speeds relative to the Sun, approximately 90 kilometers per second. Even slower stars, like Proxima Centauri, shift several arcseconds per year. A spacecraft targeting a star cluster or edge region would find that, after thousands of years of travel, its intended destination may have moved hundreds or thousands of light years. In effect, the galaxy is a living system in which everything is in motion, making precision navigation across galactic distances a constantly updating challenge. Star clusters themselves evolve and disperse. Open clusters, born from the same molecular clouds, are bound by gravity but often disperse over tens or hundreds of millions of years. Globular clusters, containing hundreds of thousands of stars, move in highly elliptical orbits around the galactic center and gradually lose stars due to tidal interactions. This means that any journey targeting a specific stellar group would contend with both the internal evolution of the cluster and its galactic orbit. Over the timescales required to approach the edge of the Milky Way, entire clusters may dissolve, altering the landscape entirely. Gas clouds, supernova remnants, and molecular clouds are also mobile. Giant molecular clouds, which serve as stellar nurseries, drift at tens of kilometers per second relative to the galactic disk. Supernova remnants expand and fade over tens of thousands of years, sometimes spanning dozens of light years. A region considered empty at the start of a mission may become filled with dense gas or radiation hazards decades or centuries later. This constant motion and evolution make route planning extraordinarily complex, as the interstellar medium itself is reshaping the path while the spacecraft is in transit. Even the galaxy's outer regions, which might seem relatively static, are dynamic on cosmological timescales. The halo contains streams of stars from disrupted dwarf galaxies, remnants of past mergers such as the Sagittarius dwarf elliptical galaxy, which has been torn apart over hundreds of millions of years. These stellar streams move across the halo, altering the local gravitational landscape and introducing additional navigational hazards. Traveling to the outer halo, therefore, involves predicting the motion of these streams over millennia, a near impossible task given the uncertainties in mass distribution, dark matter, and perturbations from other satellites. Dark matter further complicates the picture. While invisible, it dominates the mass of the Milky Way and shapes the gravitational potential. This invisible halo exerts forces that subtly alter the orbits of stars, gas clouds, and clusters. Over thousands of years, trajectories calculated without accounting for dark matter would deviate significantly. The edge of the galaxy, defined in part by the density fall-off of stars and gas influenced by dark matter, is not a sharply delineated boundary, but a diffuse region shaped by forces that are constantly in flux. A target location that appears reachable today may drift or even merge into another structure long before any spacecraft could arrive. Supernovae and stellar evolution also modify the galactic environment. Massive stars live fast and die young, exploding as supernovae in millions of years, leaving behind neutron stars or black holes. A region considered safe at departure may host newly formed energetic remnants thousands of years later. Similarly, star-forming regions constantly create new stars, altering local gravitational fields and radiation environments. The edge is not a static line, but a zone subject to continual transformation by the life cycles of stars. Even the concept of a fixed edge is complicated by the motion of the galaxy within the local group. The Milky Way orbits the center of mass of the local group, along with Andromeda, the Triangulum galaxy, and dozens of smaller galaxies at speeds of roughly 600 kilometers per second relative to the cosmic microwave background. Over hundreds of millions of years, the Milky Way itself will shift position, further ensuring that any predefined boundary is effectively unattainable. From a traveler's perspective, the galaxy is moving beneath them even as they attempt to reach a fixed coordinate. The motion of stars, clouds, clusters, and spiral arms results in a continuously changing galactic environment. Even ignoring propulsion and radiation limitations, a mission to the edge cannot rely on static maps or predetermined coordinates. Distances, gravitational fields, radiation zones, and the relative position of the edge evolve over timescales comparable to or shorter than the time required for a human or robotic mission to traverse the galaxy. The dynamic motion of galactic structures affects navigation and long-term planning. Evolutionary processes spanning tens of thousands to millions of years cause destinations, paths, and stellar targets to shift, potentially altering the planned trajectory of a spacecraft during a mission. The continuous motion of the galaxy adds a dynamic constraint to interstellar travel. Even with advanced propulsion, shielding, and navigation systems, the galaxy's structures, including stars, clusters, and gas clouds, move and evolve over time. This motion requires trajectory adjustments and predictions of galactic evolution for any extended mission. Galactic evolution results in continuously shifting positions of stars, clusters, molecular clouds, and dark matter. This motion affects navigation and long-term mission planning for interstellar travel. The outer regions of the Milky Way change over time, requiring any mission to account for the galaxy's dynamical evolution when predicting trajectories. Why the edge remains beyond reach. After examining the intricate structure of the Milky Way, the immense distances, relativistic constraints, radiation hazards, and the galaxy's constant evolution, it becomes clear that reaching the edge is more than just a challenge. It is fundamentally impossible with any technology or methodology we currently understand. The previous chapters have explored individual barriers, from the energy requirements of near light speed travel, the deadly nature of cosmic rays and supernova remnants, to the shifting locations of stars, clusters, and spiral arms. When all these factors are combined, they form an insurmountable network of physical, environmental, and cosmological obstacles that prevent any practical attempt to reach the outer boundary of our galaxy. The first major barrier is scale. The Milky Way spans roughly 100,000 light-years in diameter, with an estimated 200–400 billion stars distributed across the central bulge, spiral arms, and halo. Even assuming a spacecraft could travel at 1/10 the speed of light, a speed more than 200,000 times faster than current human-made probes, it would take approximately 1,000,000 years to cross the place. Galaxy. Even the fastest theoretical propulsion concepts, like antimatter engines or near-light-speed relativistic drives, reduce travel times only modestly when measured against the immense galactic distances. Energy requirements escalate to astronomical levels. Accelerating a single multi-ton vessel to 90% of light speed demands energy equivalent to several times the mass energy of Jupiter. The second barrier is radiation and particle hazards. The galaxy is filled with cosmic rays, interstellar dust, gamma-ray bursts, supernova remnants, and stellar winds, creating an environment that is lethally hostile over vast distances. High-energy cosmic rays constantly bombard the spacecraft, while gamma-ray bursts from massive stars or neutron star mergers can irradiate entire regions of the galaxy in seconds. Even at sub-relativistic speeds, shielding sufficient to protect a human crew over thousands of light-years is far beyond current engineering capabilities. Long-duration exposure to heavy ions and protons would result in DNA damage, neurocognitive impairment, and ultimately fatal doses of radiation. Robotic probes, though more resilient, would still face cumulative material degradation, electronics failure, and surface erosion over the course of the journey. Radiation is not merely a technical problem, it is a fundamental property of the Milky Way itself, a natural barrier that cannot be engineered away without technology that exists only in theory. Relativistic effects and time dilation compound the challenge. Even if a spacecraft could travel at 99% of light speed, time experienced on board would be drastically different from that on Earth. For example, a hypothetical journey of 50,000 light-years to the outer edge of the galaxy would take thousands of years of subjective time for the travelers, while tens of thousands of years would pass outside. This disconnect has profound consequences for mission planning, communication, and survival. Any attempt at coordinated exploration or colonization is rendered impossible, as the civilization that launched the mission would have long ceased to exist by the time the vessel arrived. Relativity ensures that even near light speed travel cannot circumvent the fundamental separation between cosmic distances and human timeframes. The galaxy's gravitational and structural complexities further prevent reaching the edge. Dark matter, which constitutes roughly 85% of the Milky Way's total mass, shapes the orbits of stars, clusters, and gas clouds. The supermassive black hole at the center, Sagittarius A star, exerts enormous influence on nearby stars, while numerous stellar mass black holes, neutron stars, and white dwarfs populate the disk and halo. These massive objects create constantly shifting gravitational fields, meaning that any calculated trajectory is subject to change over millennia. The edge itself is not a sharp boundary, but a diffuse transition zone, where the star density gradually decreases into the galactic halo and intergalactic medium. Even if a spacecraft could survive propulsion, radiation, and relativistic hazards, it would still face a dynamic, gravitationally complex environment that renders precise navigation across tens of thousands of light-years essentially impossible. Interstellar clouds, dust lanes, and molecular regions add another layer of impossibility. The Milky Way contains vast swaths of dense molecular hydrogen, sometimes spanning hundreds of light-years. These clouds are moving at tens of kilometers per second and can produce extreme particle fluxes. Even at moderate speeds, collisions with dust and gas erode hull material and produce radiation hazards. High-speed travel through these clouds would be catastrophic, with particle impacts equivalent to repeated explosive strikes on every square meter of the spacecraft. Path planning becomes a constantly shifting problem. Regions that appear navigable at departure may transform into deadly zones over millennia. Galactic evolution ensures that the edge itself is a moving target. Stars orbit the center at hundreds of kilometers per second, spiral arms rotate as density waves, and clusters disperse over millions of years. Dwarf galaxies, like the Sagittarius Dwarf Elliptical and the Magellanic Clouds, orbit and interact with the Milky Way, perturbing stellar streams and altering local gravitational conditions. Over tens of thousands of years, the minimum timescale required to traverse significant portions of the galaxy, any target destination will have shifted thousands of light-years, sometimes into regions of higher stellar density or active star formation. The edge, therefore, is not a fixed coordinate, but a transient, evolving boundary that recedes faster than even the fastest conceivable spacecraft could approach. The combined effects of distance, energy requirements, radiation, gravity, and galactic evolution present significant obstacles. Even with speculative propulsion systems, shielding, relativistic navigation, and precise mapping, the physical scale and dynamic properties of the Milky Way introduce multiple, overlapping limitations for interstellar travel. Historical perspective illustrates the scale difference. Voyager 1, the farthest human-made object from Earth, launched in 1977, has traveled just over 23 billion kilometers, or roughly 0.0024 light-years. In more than 45 years, a tiny fraction of the Milky Way's radius. Even if propulsion technology improved by orders of magnitude, hazards such as cosmic rays, radiation, molecular clouds, and gravitational perturbations would remain and increase with speed and distance. The physical scale, cosmic hazards, relativistic effects, dynamic evolution, and gravitational complexities of the Milky Way collectively create extreme challenges for interstellar travel. Distance, radiation, time dilation, and motion of galactic structures all impose constraints on reaching the galaxy's outer regions. Hypothetical technologies such as faster-than-light drives, wormholes, or advanced shielding would not eliminate the physical and environmental constraints imposed by the galaxy. Even under idealized conditions, these constraints remain significant factors affecting the feasibility of reaching the Milky Way's outer regions.